Thanks for having me. Those of you who follow me on Twitter may know that I'm not the biggest fan of 1559. And this talk will tell you why, along with some other very important things about transaction fee mechanism design. So just to start us off, mainstream transaction fee mechanism design, by which I mean the body of work that came out around the time that 1559 was being discussed, the Tim Roughgarden paper being kind of the seminal work there, has a big problem because it ignores some complexity that exists in the real world and abstracts it away in the model. So in particular, it assumes that users are not willing to wait to get on chain. So they come in and they say, I want to get on chain in the next block. And in the model, they just go away if they don't get in. But in the real world, users actually are willing to wait. So classical models, the users care about inclusion in the next block, but in the real world, we observe that they care about inclusion over some time period. Actually, this idea of good things come to those who wait is a popular idea in ads around like the 2000s era. So there's a Guinness ad and a ketchup ad that use this idea. But the same idea is true in transaction fees. Those of you who are developers who post contracts may know that you're willing to wait some time to get your contract deployed because you're going to get a lower fee. So some transactions are time sensitive. For example, you might want a DEX trade. That's certainly time sensitive, right? You need to trade before the prices change. If you're trying to buy something at a coffee shop with crypto, you probably don't want to wait 30 minutes for that to settle. If you're playing, I don't know, poker or chess or something on chain, you probably don't want to wait too long for that. So these are transactions that are time sensitive, but there's also a lot of transactions that are not time sensitive, like simple transfers, posting on an L2, posting L2 data, contract deployment, like I mentioned. So we have multiple types of, like a lot of the uses of the blockchain are here on this slide, not on the first slide, at least today. So the goal for this paper is let's look at transaction fee mechanism design with the added complexity of the fact that users are willing to trade off fast inclusion and low fees. So we have two main results, which I'll walk you through. One of them, which I think is really important and under-considered, is that proof-of-stake networks actually have better UX. They actually have less congestion, which means lower fees, with the same demand and throughput and expected block time, which is really a surprising result. But it's basically because of the regularity of the block arrival process. And the second, which is also a surprising result, is that in the dynamic setting where users face an explicit trade-off between fast inclusion and low fees, 1559 does not converge to the same price as, say, the Bitcoin fee mechanism that we had before 1559. And this is something that if you look at the literature around the time of 1559 approval, and if you look at, like, say, Barnaby's tweets, or even if you talk to a lot of people, they say, well, doesn't it converge to the same price? Actually, Ansgar, who's the next speaker, we had a conversation at some point, and we were arguing about this, which is, does 1559 converge to the same price as the standard fee market? And actually, we're both right, because in the not dynamic case, you can prove that it does converge to the right price. And there's a recent paper about that called 1559 is like almost optimal, I think is the title of the paper. And it shows that in the not dynamic case, it does converge to the right price. But actually in the dynamic case, we show in this paper that it doesn't converge to the right price, and it actually raises more revenue than the first price fee market that Bitcoin has. So here is a quick timeline of the important events as most people see it. So we have the mainnet launch. Between the time of mainnet launch and London hard fork, we had the same fee market that Bitcoin uses now, which was basically you put in a priority fee and you pay your priority fee, and the block builder takes all the transactions and builds the best block with the available priority fees, and they get all the priority fees for themselves, right? And then in 2021, we had the London hard fork, which introduced 1559. And that moved us to the current dynamic reserve price mechanism that we have now. But there's a third important event, which is the merge, which moved us from the static block arrival, moved us from this like memoryless block arrival process that came from proof of work into the current one that we have, which is like a 12-second heartbeat. And I think that's like also very important for transaction fee mechanism design and user experience on Ethereum. So what do I mean by exponential arrival process, specifically when talking about blocks? Basically, if you look at this chart up here, it's the convergence of this arrival process. So if we say there's probability 1 that it will arrive in the whole interval, and then there's probability like 1/2 that it will arrive in the first half of the interval, probability 1/2 it will arrive in the second half. And we keep doing that and go all the way down to n equals infinity. That is an exponential arrival process. And mathematically, that is a very good model of what block arrivals looked like before the merge. So this is the week before the merge and the week after the merge. Of course, after the merge, we moved to fixed slots, and almost every time that the wait was 12 seconds, a few times slots were missed, and then it was 24 seconds. And I guess you probably can't see it, but there's maybe 1 or 2 observations where 2 slots in a row were missed, right? But almost all the blocks arrived on the dot, 12 seconds. And before, we had this exponential looking thing. So the key thing here is that exponential is a memoryless arrival process. So the expected wait time for the next block arrival doesn't depend on how long you've been waiting. So if I went to Bitcoin today and I go and submit a transaction, the expected wait time for the next block to come is 10 minutes. No matter whether there hasn't been a block for 20 minutes or not, it's still 10 minutes. Whereas if I go to Ethereum and I go 6 seconds into the slot and I submit a transaction, the expected wait time is 6 seconds. If I go 5 seconds in, the expected wait time is 7 seconds. So that is a big difference between a proof of stake blockchain and a proof of work blockchain. So just to give you an idea, proof of stake is like waiting for the subway in New York City. Like occasionally it won't come, but most of the time it comes and it comes on time. And it comes every 5 minutes or so. And proof of work is like waiting for an Uber in Dubai. So no matter how long you've been waiting, the expected wait time is always like the same. So here's our main results for this, which are that if you have a blockchain with deterministic block arrival, it has lower congestion and lower fees. And what I'm showing here is actually the bids, which correspond to the fees that users pay. And the orange lines are for the deterministic setting, like proof of stake. The blue line is for the exponential setting, like proof of work, the memoryless setting. And you can see that the orange lines are much lower than the blue lines. And actually, the difference between these two plots is how many transactions there are in a block. And we're able to solve analytically for 1 transaction in a block and for 2 transactions in a block. Once you go higher than that, the analytics break down due to some non-deterministic, like you have a quadratic formula, you have a cubic formula, you have a quartic formula, and you don't have a quintic formula, and that's like a very famous theorem in math, but that's the reason that you can't go too much higher than k equals 2 for analytic results. And if you're interested in those results, you can check out the paper. Okay, this is the next set of results that I'm moving to now, and I'm going to try to do the simplest possible explanation of 1559. Here's a representation of an Ethereum block. At 15 million gas, that's our gas target right now. 30 million gas is the gas limit. So we can theoretically go up to 30 million gas, but we're targeting 15 million gas on average. The way we achieve the target is that if the block is more than half full, we're going to increase the price for the next block. And if it's less than half full, we're going to decrease the price. And in particular, you can see the formula I put it, because there's a diverse audience here. We have the mathematical expression and the code expression. Basically, to give you an idea, if the block is 100% full, then the price will be multiplied by 1 plus 1/8. If it's 0% full, it's empty, it will be multiplied by 7/8. If it's 1.5 full, it will be multiplied by 1 plus 1/16, etc. So that's basically the update rule, and as you can imagine, it looks kind of like this. You have a slightly less than full block, the price goes down. You have a more than full block, the price goes up, and so on, as you can see. So that sounds great. We're going to increase the price when there's too much demand, and we're going to lower it when there's not enough, and we're going to find the equilibrium, right? Well, I guess we kind of did that, but it looks like there's something else going on here, which is our update rule can be too fast. And that's why we see these oscillations. So this plot is actually just 1,000 blocks, so 3.5 hours. And you can see how spiky it is. I think there's 32 spikes here, I counted. And that seems a little weird to have 32 spikes in 3.5 hours like this. I think it's hard to imagine that this is accurately reflecting like some underlying changes in demand. And it's more likely that the model is fooled by randomness in the arrival process of transactions. And that's an interesting thing, and that's going to be what leads to the result that these don't converge to the right prices. So 1/8, which is the update parameter, is too fast. And basically the way that the core dev set parameters is they just choose some like random n, and then they do like 2 to the n, and then that's the parameter. I mean, I'm being a little facetious, but actually there is like a fascination with 2 to the n, and this parameter was chosen at the beginning and like has not really been looked at too much. And I think it's too high right now. And basically, time-sensitive transactions are going to have to pay higher fees during spikes, because if you're in a spike and you're time-sensitive, like it's too bad. You just have to pay the fee. Like if you're just like at block 180 here, you just have to pay the high fee because you're time-sensitive, right? And if you're not time-sensitive, then you're going to wait for the price to go down. But if you're a time-sensitive guy, you can't pose as a time-insensitive guy because you're going to have to wait, and you're time-sensitive. So what does that look like in the results? This is going to take a second to explain, but if we have a model where there's 2 types of transactions, there's high time sensitivity types and low time sensitivity types. The load, which is the arrival rate of high sensitivity types, is on the x-axis here. And similarly for the low sensitivity types on the y-axis. On the right here is the priority fee mechanism, so that's similar to Bitcoin or what we had before 1559. On the left, that's what we have with 1559. And we have some simulations here. You can see that for the same load, the average number of transactions in the queue, as we get to stronger and stronger load, it blows up in the 1559 case. So in the top right, which is where we're almost at full load, you can see it's 6 on the left, which is the 1559 case, and 0.6 on the right, which is the priority fee case. And what that means is it's similar to like in an airline can charge more for business class by making economy less comfortable. So if they reduce the legroom in economy, then they can charge more for business class because they've like penalized you more for not upgrading to business class. And that's similar to what this looks like. So that's like the United business model. And the Emirates business model is we're going to make business class nicer. But this is like 1559 is more the United business model where they just like crush you in the economy seat and then make you pay for business class so you get more room. So just to summarize, in the dynamic model, not the static model, where users are willing to wait for lower fees, time-sensitive transactions end up paying more under 1559, and time-insensitive transactions have to wait longer, and these are necessary for each other. Otherwise, the time-sensitive transactions would be able to pose as time-insensitive transactions. And that means that 1559 actually has higher revenue than the standard priority fee model, which is not something, if you remember at the time, 1559 came out, fees were really high, and people were really mad about it. And actually, a lot of people said that 1559 would lower fees, which obviously was not true. But if you said 1559 is going to raise fees at the time, I don't think it would have been very politically palatable. So it's interesting that we find this out now that it actually does raise fees because the update parameter is too high. So if you're interested in what can we do about this, in the spec, which you can read about on our website, mechanism.org, we talk about a special mechanism called dynamic VCG, which is a way to do an alternative to 1559. And we also talk about how to update the update parameter for 1559 to be slower so that we don't run into this issue. Thanks for coming, and thanks to the organizers for having me.
Awesome. Yeah, check out his PDF.